Okay, so can everybody see the slides? Can you see the slides and the transition?
For me, it's stuck.
It's stuck. Okay, remind to wait for a few seconds. Still didn't show up?
It's stuck on like your PowerPoint screen. It hasn't just shown the slide.
It's weird. Let me do it again. Sometimes it's like this. Okay, so does it show up?
It's still loading.
Okay. Seems that there's a networking issue, right? How's it right now?
Still loading.
Come on. Okay, so let me, before it is still loading, let me first emphasize the point in the homework. I have summarized several commonly issues I've seen during my office hour for homework too, especially the implementation of ADA boosting. So several students came to me and complained that they are not able to show their ADA boost, kind of like uh, uh, quickly reduce the training error, then make the training error stable while the test error exhibits the same kind of behavior. This is typical for correctly implemented ADA boost, meaning that the test error are much less sensitive to the overfitting issue. So I have summarized several cases which I am saying, and hopefully that will help. But here I just want to emphasize, if you are frustrated with the debugging, actually this is very important in practice. So you may have you might have got sense, right? So it looks like when we go through the slides and introduce the idea, the algorithm steps, all kinds of stuff that listed here, it's pretty clear and it's pretty straightforward, and everybody feels comfortable. However, when you implement it, when you test them on some actual data set, you'll feel some burden. You might be annoyed by a few bugs or something that might be like a small tiny bugs, right? You didn't realize that, and then it just cannot work. So that's the major motivation for the practice problem. We're not This is not a course that give you a general brief introduction of machine learning, and then you can get a grade A. That's not possible. So everybody should really experience what is machine learning, how it is used in practical applications and data set. So the debugging is very, very important step. We assume that everybody has some kind of experience in programming and debugging. So if you feel no clue on that, please take advantage of these office hours or Piazza and state your problem. We can try our best to give you like suggestions, hints on that. However, the debugging itself must be done by yourself. Like just use all kinds of tricks in your hand. Like you can do it step by step, step in, step out. Each function you have implemented and check out the variables and see if there's any anomaly. Right? So if it is I mean, if there's no other way, don't try to let TMs to help look at your code line by line. You know, even machine learning researchers like me and my students or other TMs, when they implement their own model, like their implement code, they cannot guarantee it will be correct. We need debug as well. So the common use way is that, okay, we first look at the code line by line, but even we ensure that after we scan our code, we feel it is correct, it does not guarantee the code is correct. Well, we have also to do the debugging. So try to print out all the intermediate results, examine their values at each step for a particular case, and to ensure there's no abnormal behaviors. And that rather than just to look at code line by line, right? Even you ask me to help you read the code line by line, if I cannot find any issue, that does not mean that your code is okay, that code is correct. You need to use all kinds of tricks you have used before to debug your machine learning code as well. Okay. So any question or complaint about the practice problems, your homework?
So I'm running into the problem of it's taking too much time to actually run the code for 100 bags and 500 trees each. So for calculating the sample variance and sample bias, for that experiment, it is said that we should create 100 bags with each bag having 500 trees.
Yes, yes.
I ran that code probably like 16 hours back, and it's still running and it's halfway done, but I don't think it will be done by the end of the day, like when I have to sum, so I won't have that bias variance. So my question is, can I run a smaller experiment? I think it would give the same result, like with 20 bags and 100 trees in each bag.
No, you won't get the same results. Yeah, the reason I asked you everybody to run like 100 bags where each bag contains 500 trees, all kind of stuff, to ensure that you get like pretty accurate estimate of this plus the variance trade-off estimate. Otherwise, you won't. Otherwise, if you get only 20 bags, it won't give like reliable estimate with the strong statistical power. And the second thing is that, sorry. The second thing is that it takes some time to run, of course. But you said you have a run like for how many hours, Tisha?
Oh, it's been like 16 hours now.
16 hours. That is mainly due to your implementation is too inefficient.
Right.
Yeah, the reason I think I have seen such a discussion in our Piazza, right? So try to use the NumPy array to store everything, update them with matrix and vectors, rather than do the for loop inside each feature. If you do that, it's kind of really really slow.
Okay.
Another thing you might feel helpful is that you actually do not need to sequentially run all the bags and get all the trees. If you have like parallel computing power, like if your computers have like multiple cores, like 20 cores, 16 cores, you can try to do them in parallel, but be sure to use different random seeds. Otherwise, you get the same tree for each one.
Okay.
Yeah, I would suggest you to just quickly revise your code, right? Not to plug in a for loop everywhere. Otherwise, you really need a long time on that. And those kind of things can get worse even when when we talk about linear least mean square error and linear classifiers learning algorithm we'll implement later. So try to calculate the information gain, all kinds of stuff, so using vector and matrices rather than performing the follow.
Okay.
Okay,
Yeah.
hopefully that was helpful. And I will try to summarize some kind of like debugging tricks, which I assume everybody uh, has known these tricks, but here I just want to emphasize that and also remind everybody, like if you feel like confusing and feel like time consuming to get those code working, try to reference those tricks and use those tricks to solve your problem. Okay, so now uh, uh, can I get your I mean uh, are you able to see the slides right now?
Yeah.
Okay, great. So it takes a while. So how about the transition?
Yes.
Is the transition of the slides okay?
Yes.
Okay, great. So let us continue with perception. Today we're going to first wrap up the perception topic. That means our homework 3 will come very soon. But this is a kind of like pace our course goes on. So this is not an easy course, but hopefully everybody is going to benefit from this course. Okay, so in the last lecture, um, we have introduced some theoretical guarantee about perception. Right? We know that when the data set is linearly separable, then when in whichever order you feed your training algorithm to the perception, it will guarantee you to find a separating hyperplane, right? So the specification of that convergence behavior is called Misty-Bound theorem, right? We not only can claim that our perception will converge finally, but also can give some kind of estimate, right? On the upper bound, the finite upper bound of number of mistakes or updates made by perception before the convergence. And also another thing we need to be aware is that if the data is not linearly separable, then if you run perception like forever and ever, you see that it will finally enter into an infinite loop, where each loop it just cycles through a set of distinct vectors. So unless you set a threshold of the maximum number of updates, it will never stop. So we mainly talk about all the details about proof of Misty-Bound theorem, right? So here I just want to use this figure to summarize it and to highlight the insight and the intuition behind that. So suppose we have this uh, green and red examples of our data set, and those data set, their features are kind of finite, meaning that we can always draw a circle or a ball which include all the training examples. To get such a ball, it is relatively easy. We just look at which point, right? Which training point is the farthest from the origin, right? We just use that training point, right, to draw a line to the origin, right? Those lengths of the Euclidean norm of this point is actually the radius, right? R. Right? We call R as radius or maximum range, whatever. Right? But anyway, this R specifies what is the largest span of the whole data set. And meanwhile, we assume that for this data set, there is a separating hyperplane whose margin is gamma, right? So remember, what's the definition of margin? Margin is the minimum distance between the training points and the separating hyperplane, right? So given this maximum span R and the margin for an arbitrary separating hyperplane for this data set, we can claim that when we run perceptron, the maximum number of mistakes or the updates of the perceptron is less than or equal to this number, right? R squared over gamma squared. So you just divide R by gamma and take square, you get the finite estimate of the upper bound of the mistakes made by perceptron, right? So remember, perceptron only updates when it makes a mistake in predicting a training example. So the number of mistakes is same as number of the updates. So as we discussed before, right? This is actually just give us some kind of intuition and how many updates the perceptron can make, right? But this is a very rough estimate or very rough upper bound. Why? Because you can choose an arbitrary separating hyperplane. I can draw another separating hyperplane. Sorry, so it should come across the orange, right? And you have a different margin gamma pi. You can use gamma pi in R to construct another upper bound. Right? So you have you have an infinite number of the upper bound of the mistake, right? So actually, the actual number of mistakes made by perceptron is actually minimum of all the possible bounds, or a more rigorous speaking is kind of like infinimum. This is a mathematical term. Infinimum of all possible upper bounds. And we talk about how to prove this bound, right? We use 3 steps. First step and second step prove 2 different inequalities, and third step we just combine these 2 different inequalities through the Cauchy squares inequality, and then we solve that inequality, like left hand side, right hand side, and then we get this bound. So any questions so far in understanding this Misty bound theorem? Because this is really important. We're gonna apply this bound, this theorem to estimate some practical problems, and also to prove some kind of variant of this theorem. Okay, it seems everybody feels comfortable. And then we showcase an example, right? Suppose we want to learn a disjunction of n variables. We know that this function is totally linearly separable, right? We want to estimate if we use perceptron to learn a linear classifier, what is the upper bound of the number of mistakes, right? So we just do 2 steps, right? First step, we just find a maximum span, right? Remember, we need to assume all the inputs are the input vector is augmented with constant feature 1. That's where this R comes from, right? And then we talk about how to find a separating hyperplane with a non-zero margin, right? We first reviewed our previous trick that from the definition of this Bloom function, we can directly construct a separating hyperplane. However, this hyperplane has margin 0. Why? Because some data points directly stay on this hyperplane. That means we cannot directly use that to construct a bound, because margin 0, then your upper bound is simply infinity, which is not meaningful, right? So we need to adjust the position of this hyperplane a little bit to ensure that no points rightly stay on the hyperplane. And I just gave one number, like by replacing this plus 1 by half, then we can ensure this point. And we can calculate the upper bound correspondingly. But actually, you are free to choose any other number as long as you do not have any data points stay on the hyperplane. Okay, so regarding perceptron Misty bound, everybody needs to know how it is proved, and needs to know how to use that to get a rough estimate of the updates when you run perceptron for a particular data set. So, so after this some kind of theoretical analysis about perception, right? The remaining topic is about practical variances. Right? We know that the theory and practice is always, always have some gap between them. Like we're gonna first talk about in practice how do we implement perception, standard perception, and also to further improve the generalizability and also reliableness or robustness to outliers, noises. How can we implement perception? Okay, so we're gonna first talk about how we implement standard perception with finite data set, right? So we know that practical data is always finite. That means you have to designate running how many times, how many updates our perception is gonna stop. Right? And then we'll talk about two practical extensions of perception. One is to generalize perception to be better, right? How can we further improve the prediction performance of perception predicting future examples? A second type of generalization is, or extension, is how to deal with outliers, noises in those data, in particular when the data is not linearly separable. That we're going to talk about the multi and averaging perception. Right? Okay. So first, let us look at how in practice we should implement the standard perception. So here is the algorithmic framework. I suggest everybody to follow these steps to implement your perception in our homework 3. Right? So at the beginning, we assume, okay, we have observed a finite training data set, xi and yi, where each training input xi belongs to the n-dimensional space, while I is either -1 or +1. Right? So here again, I want to emphasize another 1,000 times, xi has already been augmented with constant feature 1. Right? Don't be confused. And at very first step, we're going to initialize our weight vector to be the 0 vector. Remember, the weight vector includes both the feature weights and the bias bracket. So we're going to initialize them all to be zeros. And then we're going to go through the whole data set for big T epochs. So T here is some hyperparameter to the algorithm, which need we to set up beforehand. So the epoch actually represents the number of passes you're gonna go through the data set. One epoch means that you're gonna go through the whole data set once. And then inside each epoch, we first shuffle the data. And to get a different random order. And then we stream the training examples to our perception, right? And then when we look at each training example, we just make predictions, say if our prediction is correct or not correct. And if it is incorrect, we're going to update our weight vector according to the perception rule, right? This is the rule we have mentioned many times, right? And if it is correct, we're going to look at next example until we finish going through the whole training data set. That means we have finished one epoch. Now we look at next epoch. We do it again until all the big T passes or epochs have been finished. Then we return the final W. So here, in practice, we often use this inequality to test if our prediction is correct or not. Rather than I'm gonna first take the sign of this inner product, which is sign of the prediction score, and compare this sign with the ground truth label, and then decide to update or not update. So this is a whole algorithm steps to implement the standard perception in practice. So any questions so far before we get down a little bit more details?
Sorry, I think you mentioned this, but could you explain again what shuffling the data means?
Oh, shuffle is just means you just randomly permute the data samples.
Okay.
Nothing else.
Okay.
Yeah, basically, it's just want to just want your weights to be updated in kind of like random balanced way rather than you just fix the order and again.
Okay. And so, and also, I guess like this seems like, I mean, in a lot of ways, this seems very similar to this LMS regression
Yes.
algorithm. Okay.
Yes. Very good observation. We're going to discuss later when we talk about when we systematically compare with gradient descent and stochastic gradient descent. We'll show that this actually is another version of stochastic gradient descent. But here I'll just hide the true objective. This is essentially to minimize some objective function with stochastic subgradient descent, and those is the stochastic subgradient. But I'm gonna discuss later. Any other question? Okay, so yeah, I just want to highlight a subtle point, which is different from the previous standard version of what I'm saying, like for the perception rate. So remember, in our when we first introduced the algorithm for perception, we're gonna first use in each when we deal with each training example x, y, y, right? We're gonna first look at the sign of the prediction score and then compare the sign with the ground truth label, right? But here we just use this inequality. So there is still some difference here. So I don't want to confuse you or someone might come to me later and I want me to clarify. Right? So here there's a subtle difference. Hopefully you're going to be aware of. So remember, if we just do the prediction right with the label right, and this label comes from the sign of prediction score, we compare the label and if their label are different, their label is different, we make an update. Right? There's a if we use this equation to decide, right? So if you want this updating cases, the cases of this updating right, incurred by this inequality to be exactly the same as the previous way of determining whether we're going to update or not, right? We shouldn't use this less than equal to. We should use less than. Why? Because consider a case. Right? This is our current hyperplane determined by the current rate vector, right? So if there is a positive example, training example stays on this hyperplane, and this is x, I, y, I. And then, according to the previous way to implement perception, right? We just take a sign of this W transpose X. The sign will be positive, right? And we know the ground truth label is positive as well. So that means we do not need to update W. That means we don't need to change the position, the angle of this W. But here, in our case, this product will be 0. Why? Why this product will be 0? Why W transpose X?
Because it lies on W.
Yes, exactly.
And
right.
So really the vector along W is always going to be perpendicular to W.
Yes.
Because well, I guess W is the normal vector, but if it's on this plane, then yeah, it's always going to be normal to it. So
yes, exactly. Right. So remember, this is the mathematical formula which represents this hyperplane, right? So if the point stays on this hyperplane, you must have this equality host, meaning that remember W is perpendicular to the hyperplane. Right? The inner product must be 0. That implies that if we apply this testing condition, no points can stay on this line or on this hyperplane. Even you use it to predict and the label is correct, you're going to still update the weight vector to ensure that after update, your weak vector does not, your hyperplane will not have this point stay on it again. So this is a subtle difference. So for the previous implementation we have seen, right? The previous algorithm we have seen. Okay, if we just take a look at the sign, we just apply the prediction rule, right? We get a label and compare with the label. Then for this case, if a positive example stays on this hyperplane, well, you're gonna ignore the update, right? Because it's correct, right? We're gonna look at next example. But for our current implementation, which I suggest you to follow that in your homework, even in this case, right, even your prediction is actually correct, you're gonna move your W a bit to ensure that you won't have any examples to stay on this updated vector. And now I want to ask why. Or do you think there should be any preferences over the two approaches? I mean, one is just to compare with the label. The other is just have you apply this test condition. Any thought? It's fine. I mean, if you don't like this one, just let me know. It's fine. Okay, so let me explain 2 points, right? So first, we have to use this less than equal to. We cannot use less than. Why? Because remember, we initialize our weak vector, including the bias, to be 0, right? That means whatever example we first look at, right? This value is always 0, right? It's always 0 because initially W is 0, right? And then if you use strictly less than, right, it will mistakenly assume that, okay, you're making correct prediction, right? Because this include does not hold, right? It won't incur any update. Then you look at next example, your weight vector is still 0, right? And then you calculate this left-hand side is still 0, and 0, of course, is not less than 0, right? 0 is equal to 0. You're gonna not incur the next update. So if you don't apply this less than equal to 0 here, you will not be able to incur any effective update. That's one reason. That's one reason we have to use less than equal to 0, right? Of course, someone may argue that, okay, why not I use this include? I just just compare with the labels, right? One label comes from our prediction by taking the sign, right? And the other label comes from the ground truth. We just compare. If there is any difference, we just incur the update. Yeah, that is true, right? But the second thing is more important. We find that, like, by following the previous algorithm steps we mentioned, right, it actually tolerates the case that some positive example stays on the line, right? However, by contrast, if we stick to this principle, right, if we keep using this test condition and decide to update or not, right, after convergence, there will be not any example staying on hyperplane. Then the question is, it is better to have our hyperplane be away from any training examples, or suppose you have 2 choices, right? One hyperplane passes through one or few training examples. The other is away from all the training examples. Which one do you like better?
away from the examples.
Why?
Because then we, yeah, I guess as Jacob said in the chat, it's actually separating your data. It's giving you, it's I guess, I don't know a better way to put it, I guess.
Yeah, you're right. I think I appreciate your insight on that. Right? And actually, Jake's insight is correct as well, right? So now this is a very important problem we're going to discuss right now. But here, I just want to give you some conclusion. It's better to have your hyperplane to be away from the data set and to be the further away, the better. So why? Let us look at some more analysis, right? So that also the motivation for this so-called variance called margin perception. So let us look at some concrete data set, right? So here's a positive and negative examples. Obviously, those examples are linearly separable. We have like numerous separating hyperplanes, right? So suppose we have just a random pickup two hyperplanes, H1, H2. Right? So obviously, these hyperplanes have different margins. So now, the question, I mean, from the previous question, right, can be generalized to like, if you are asked to decide which hyperplane or linear classifier is gonna give a better generalization performance, what's your decision? Like, what's your preference? I believe Jordan and Jake will definitely choose H1, right? Because they are farther away from the training examples. But here I want to hear more thoughts, and if anyone can share your thoughts or intuition, please feel free to share with us. Any thought, any comments?
Blue one.
Everybody agree with?
Blue is more generalizable because sort of it's equidistance from both the sets.
Yeah, but why this from examples so that it is it generalized better? Any thought about that?
Isn't it because it just improves our mistake bound theorem by increasing the denominator? So that if we can bound the maximum lower distance, we can have a smaller margin of error.
Oh yeah, you're talking this more depth. Yeah, we will come to that point. But here I just want to yeah, you're right. But for that part, we're gonna mention some kind of analytical results when we discuss about margin classifiers, max margin classifiers like spot vector machines. But here I want to explain in a more intuitive way, right? So that everybody can feel okay. Right? It should be better. Right? So why should we choose H1, right, rather than H2? So from the data distribution, what we can see is that okay, here and here are the points where positive negatives comes from. So naturally, the more frequent where a place that the examples appear, the higher the density. So you can imagine that actually the training points, they kind of gather around their high density regions. So if a hyperplane is too close to the training examples like H2, right, it is more likely to pass through the high density regions. It's like H2, right? We can see that, okay, it passed through the high density regions for positive examples and high density regions of negative examples. And then what is the consequence if your hyperplane kind of pass through those high density regions? So you can imagine if you use H2, to predict some future example. If this future example is positive example, it is more likely to appear in the high density regions, meaning that it is likely to appear here. Of course, it's also likely to appear here. However, if those positive examples, right, appear on this side, H2 will make wrong predictions for sure, right? Because it classifies all the examples on the other side. If the positive examples appear in the other side, on this side, it will be predicted as negative example. Similarly, H2 seems to pass through this high density region for negative examples as well, right? So if the future example H2 is going to predict are some negative examples, it is very likely that you have seen some negative example on this side. Of course, H2 would make again. So you can see that if your hyperplane are too close to examples, it takes much more risk to pass through the high density regions. And then it is more likely you're gonna say some future examples kind of like perturbating around the separate. In this case, you have more risk to make mistakes, or higher risk to make mistakes.
I have a question about that. So could you make an argument then that like H2 is essentially overfits the training data in a way? Because
no, it's not overfitting, because both H1 and H2 have 100% training accuracy.
Oh, okay, I see what you mean. You're just saying it's just going to be, I guess I don't know the right, yeah, it's just probably going to have less prediction accuracy.
Yes, in
H2.
Sure.
Yeah,
so,
okay, I see.
Yeah, it's not always overfitting issue. It's just about like, okay, if I'm a same, if you're what kind of classifier is more favorable predicting future things? We'll see that actually the classifiers, linear classifier with large margin, belongs to a simpler classifier, where that means your model complexity. That will lead to another justification of the, Occam's razor principle. But this have nothing to do with overfitting.
I see for sure. Okay, cool. Thank you.
Okay. So let me finish this a little bit, and then I will ask a question to ensure everybody is clear about that. So we have seen that because H2 are so close to all the training examples, it takes higher risk to pass through high density regions. As a consequence, those examples with the same label have a much larger chance to appear on both sides of the hyperplane, right? So that means H2 is more risky to make wrong predictions. And by contrast, right, we see H1. Right? H1 is further away from both training and test examples. So it's very unlikely that H1 is gonna go through or nearby the high density regions. So if we use H1 to make predictions for so it is highly unlikely that some positive example will appear. Why? Because here low density region. So in most cases, like positive examples will just show up in this ellipsis area, right? It is very unlikely that some new positive example showing here. That means H1, the chance it makes wrong prediction is very low, much lower than H2. And similar arguments apply for future negative examples. But we know all negative examples should show up in their not all, like will like mostly like highly likely appear in the high density regions around here, right? It is highly unlikely that some like negative example show up here to make H1 predict incorrectly. So now we can see that because H1 is kind of further apart from both positive and negative examples, it is further from the high density regions, or is the cases some like the cases that examples of the same label appear on both sides. So intuitively, that's why a larger margin classifier usually gives a better generalization accuracy. Any questions so far? So is everybody comfortable with that? Okay, sounds great. So it looks like it's quite intuitive, right? But as some of you have mentioned, this is not like can be intuitively. It is can be theoretically rigorous proved by by theory. We'll see that later when we discuss about fallback machines. Uh, we'll see that large margin classifier can give us a better generalization error bound. And you see the margin actually determines the generalization bound. Okay, so now we want to incorporate our insight into some kind of extension of perception, which is called margin perception. Right? So how can we modify the standard perception to be a margin perception? So in our previous discussion about the implementation, right? We use this inequality to decide if we're gonna update our hyperplane or not, right? And namely yi times w transpose xi less than or equal to 0. If this inequality holds, it means that okay, you're gonna make a wrong prediction, so you need to if you haven't made a wrong prediction, you have to adjust the weak vector, right? But here, the margin perception just modify this inequality. We first pick up a positive it must be bigger than 0, and then for an arbitrary example xi and yi, we're gonna first test if this inequality is correct. Like if this inequality holds, we incur the update. Otherwise, we just move to the next example. That's it. So now I want to ask, what does this inequality mean? What does it reflect? Is it a more relaxed version of this or more restricted version of that? Any thought?
I mean, it seems to be a little bit relaxed in that, like, you can include more examples that are positive as long as they're close to some threshold n, right?
So do you think it's more relaxed? But from what you say, I feel it's more.
I don't know how to say if it's more relaxed or less relaxed, but it seems like it includes positive examples now, so long as they're like less than a threshold.
Yeah, it should be viewed as a more restrictive.
Restrictive. Okay.
Any other thoughts? Any other comments on this new testing condition? Okay, so first let us look at compare with this, right? Is this a more rigorous or more restricted version, right? So, so first we would like to look at if if this inequality happens, when this inequality is holds if this equally happens as well, right? So if this product is negative, of course this product is negative as well, right? Because yi w transpose xi less than or equal to 0, numerator is less than or equal to 0, and remember the norm of w is always positive, right? So this equation must hold because eta is positive as well. That means, okay, if you make incorrect prediction, you will definitely incur the update with the perception rule, right? So it's the same as the standard case. However, even your yi w transpose xi is bigger than 0, you still have some kind of possibility this inequality does not hold, right? So if it is bigger than 0, however, this value is still smaller than eta, you're gonna still incur the updating rule, right? You're gonna still adjust the position and the angle of your hyperplane. So this is actually make more updates, make more possible updates than the standard perception. So if you make wrong prediction, you're gonna inevitably update your weight vector. This is the same as standard perception. However, even you make a correct prediction, but this number, this fraction is still less than this threshold eta, you're gonna still adjust it. So now we want to know what does this mean. If we remember what we have reviewed, the definition of distance, this is actually the distance. If w correct predicts x and yi, we know this product is positive, and divided by the vector of w, this is actually distance between xi and the current hyperplane determined by w. So this test condition tells us that even you can correctly predict xi, if the distance between xi and the vector, the hyperplane determined by w, is less than this threshold, you're gonna still adjust the hyperplane to ensure that xi is at least eta away from the hyperplane. Right? So let me So suppose this is a current hyperplane, right? Determined by w. W is orthogonal to this hyperplane, right? So suppose this is your current xi, right? So in a standard case, right, because of course yi w transpose xi will be bigger than 0, right? It doesn't need to incur any update. But for here, so left-hand side actually is the distance between this positive example and this hyperplane, right? If this hyperplane less than eta, we're going to still update the weight vector to ensure that the distance between this positive example and the updated weight vector, the hyperplane, is bigger than eta, or no less than. So imagine that after convergence, all the training examples will be at least eta away from the separating hyperplane. What does that imply? Connecting to our definition of margin, right? Actually means that, okay, after convergence, the margin of our learned hypothesis or learned hyperplane is at least eta, right? So actually, eta is the threshold of the margin. That's why this is called margin perception. Any question? You understanding the idea?
Yeah, so it's like saying we're going to update now if it incorrectly predicts, or if it correctly predicts, but that correct prediction is too close to the
Yes.
hyperplane. Then we're just going to update so that we can make sure that all correct predictions are going to be at least some distance eta or whatever. I can't remember the name of that letter. It's going to be some distance from the hyperplane, and that's what will guarantee this margin.
Yes,
Okay.
exactly.
Cool.
Yeah, that's the key idea of margin perception. From our previous analysis, we know that the further away the hyperplane from the training examples, the better the generalizability, right? So of course, the way to measure how far away your hyperplane from training example is the margin, right? Remember, margin is the distance, minimum distance from the training points and the hyperplane. So the larger the margin, the better the generalizer error, right? The better generalization accuracy, right? But although, I mean, that's how this motivates the so-called margin perception, right? which is expected to improve the generalization accuracy. However, I mean, there's no free lunch. Right? We have to carefully choose eta. And why? Consider that if your data set, remember, the data set itself has a margin, right? The margin of the data set is actually the maximum margin of the separating hyperplane for that particular data set. Right? If you choose the eta to be too large, right, even beyond the margin of whole data set, you'll never converge, right? Because there's no such hyperplane which has its margins bigger than this upper limit. Right? So a good practice is gonna set eta to be 0 at first. Right? So that it will be reduced to the standard perception, and then you just increase eta, right? Until in some point that when you increase the eta, it can now converge at some designated number of epochs, designated number of epochs to stop. You pick up the largest available margin eta you have tried. Okay, this is about a margin, like margin perception, which is used to further improve the generalizability of perception. So next variant we're going to discuss is about how to improve the robustness of the perception learning algorithm. Right? We know that in practice, data are not always guaranteed to be linearly separable, right? In many cases, it could be like almost linear separable, meaning that, okay, we can linearly separate most positive and negative examples. However, there can be some outliers or noises, like the two positive examples here, right? We fail to separate. In such a case, how can we modify our implementation of the perception to ensure that we're much less sensitive to those outliers and still can get kind of like well-performed separating hyperplane, which can give a correct prediction for most of the examples. The straightforward approach will be like, let us just find a hyperplane, right? Who has minimum mistakes in the trained data. Right? Suppose I want to find a separating hyperplane, the black line here, right? We only have 2 prediction mistakes. However, when you just run the standard perception, you might have a different hyperplane, right? You might go through many hyperplanes. What different hyperplanes will have a different training error, right? And then I just look at the hyperplane which has minimum mistakes. Well, this can be like a way, but it's kind of like be hard, especially if you want to do the exhaustive search over the whole family. So to get a more practical version, we often use this framework, which is called vaulted perception. So what is voltage perception? So we just go through like big T epochs. Remember, T is the hyperparameter set by users, right? And then when we go through during the whole perceptual learning procedure, we're gonna record every distinct weight vector we have seen. And meanwhile, how many times each distinct vector was used to make predictions. And finally, after this big T epochs have been finished, we're going to return a list of distinct weight vectors and their counts, namely the number of predictions made. So here is the algorithm framework. So the outer level is the same. And inside each epoch, and when we go through each training example, right, if our prediction is incorrect, right, we update our weight vector, meaning that we need to create a new version of the weight vector. Right? So that's where we should increase the index m by 1, and then we assign the count, the number of predictions, by 1. If the prediction is correct, right, not incorrect, it's correct, right, we just increase the count of number of predictions made by the current weight vector because there's no change of weight vector. And why do we initialize the count Cm to be 1 rather than 0? The reason is that after each weight vector, when it makes the first mistake, it's going to be updated to a new weight vector. Right? But that mistake should also be counted as one prediction. Right? However, according to this updating logic, right, we're not able to update the current weight vector's count. That's why when we create a new weight vector, we add this count 1 at the beginning, so that when it makes the final prediction, namely it makes a wrong prediction, we do not need to add this count anymore. We just create a new weight vector and create a new variable to record its count. So that's whole actual steps we're gonna need to implement our voltage perception. So any questions so far? You understanding the algorithm steps? Is it reasonable for everybody?
Yeah, is it incorrect to draw a comparison of this to like Ada Boost?
No, this has nothing to do with Ada Boost.
Because it just seems like it's a similar concept where we're saying essentially we have all of these different classifiers, and then have a weight term that says how accurate was it, and then we use a combination of all of those.
Oh yeah.
To make a final prediction.
If you will, in that high level, yes, it's kind of like similar at very high level. So actually,
but the inner workings of it, are very different. Okay.
Yeah. It's equivalent to saying, okay, we're gonna use ensemble learning, right? It's a kind of ensemble, right? Ensemble of all the possible weight vectors during the running of the perception, right? And then we're gonna use the number of the predictions to measure how important the prediction made by this particular weight vector, right? So of course, right, the more prediction it makes means the more frequently this weight vector predicts the training example.
Right. Okay.
And then after we have collected this weight and count pairs, finally, and when we use them to make prediction for a new training example X, new test example X, right? We're gonna first use each distinct weight vector to make prediction. So take the sum of the prediction score, right? And then vote their prediction by the current CI.
Yeah.
And then finally, we just compare the counts of the total votes of the positive predictions, negative predictions, and pick up the one who has the final larger vote.
Right.
And this part is exactly the same as A doubles.
Right. Okay, cool. Thank you.
Okay. Any other question?
Yeah, I'm a bit confused, or not confused, but just wondering about C here. So for CM, it's kind of just like the number of mistakes that you're making, right?
Oh, it's not a number of mistakes, it's number of predictions, or number is correct predictions you make.
Okay, number of correct predictions. And so at the
sorry,
end,
it's
when
not
we're
it's just a total number of predictions, it's including all the correct predictions and the one wrong prediction.
okay, so with that in mind, when we're making the final prediction at the end, and they're kind of you're multiplying by whichever kind of step that you're on, whichever C that you're on. How come it seems like at the very end we were weighting all of our weights of the predictions at the end when C is high much more heavily. So I'm wondering what the kind of theory or background behind that is.
Oh, you mean the intuition theory? We're not gonna discuss the theoretical guarantee about this, but here I want to give you some intuition behind this. So look at this, right? So actually, we want some final prediction which can give the correct big prediction for most of the examples, right? We can ignore those incorrect predictions. Sorry. For these two examples, right? We just want to ensure the majority of the examples are correctly predicted, right? But if you just run the standard perception, you actually do not know when this hyperplane will stop, right? It is very likely that this hyperplane is highly affected or influenced by these two outliers. And as the cost is that, okay, it might be finally it can predict all these two outliers, but fail to predict many other positive and negative examples. But here in voted perception, the benefit is that, okay, if one hyperplane, it can predict most of the examples, right? Your C values will be quite large. But it also accounts for those those hyperplane which can correctly predict those outliers, right? But because if it can meanwhile incorrectly predict other many other examples, their weight or their counts are small. And we just integrate them together to ensure that, okay, for those hyperplanes which can correctly predict most of examples, they will be voted most. Right? They have a largest importance. Their prediction will compete over will beat those classifiers which can only take care of outliers.
Okay, I think that makes sense.
A more robust, more reliable classification result. Imagine that if your data set, like you have 10,000 examples, right? But you don't want like 2 outliers to ruin your classification of 1,000 examples. That's where this voted perception wants to do.
All right, thank you.
Okay, any other question?
And one other just implementation detail. So before this loop, then CM would be, you might have said this earlier, CM would be initialized to be 0. And then when we come in, but then once we update WM, it's not reset to 0, it's reset to 1.
No, M is actually increasing, right? So actually C is a vector. You should use a vector to record all the C values. So this is C1, C2, blah blah blah.
Oh, okay.
So at beginning for C1, you might set it to be 1, right? If it is correct predicting two examples, just increasing the value in the cell, right? 3, and then you get C2 is 1, blah, blah, blah.
Okay.
And also you need to create a list of these vectors, right? Or array on that as well. I don't know, because, but anyway, for each distinct weak vector, you should allocate some kind of long vector or long vector list to store the values, right? When you have a new weak vector, that is
Right.
that happens when you update, right? You get W2 and etc.
Right. Okay. Sounds good.
Okay, great. So although voltage perception is kind of intuitive, right? It just reflects the ensemble learning idea, high-level idea we discussed, right? But in practice, it's kind of like expensive, mainly in the storage, right? We need to keep track of all the distinct vectors, right? And also, for each distinct vectors, we need to use an actual variable to state to count how many iterations it was used. Right? This is kind of costly, especially when we deal with a very large data set where you might have like millions of distinct vectors. So here comes a more practical version or more efficient version. It's called average prediction. So the average prediction is just a tiny modification of the standard implementation of perceptron. So we just introduce one extra lead vector, A, and initialize A vector to be 0 vector as well. And A and W, they have the same dimension, same number of dimensions or same number of elements. And then going through big T epochs and random shuffle the training set, which we note here. And then we go through a training example. And when we make wrong prediction, we update according to perceptron rule, right? That's it, right? This is the same as the standard perceptron as we discussed, right? We only need to add one line of code. That is, no matter you update or not, you just add the current weak vector to A. That's it. And after you finish all the epochs, you just use A as our final weak vector, meaning that for arbitrary new past input X, we just use A to make prediction and take the sign of the prediction score. That's the average perception. So it's much easier, more convenient to implement than voltage perception. So now I want to point out the connection between the two, right? So actually, this line of code adds all possible W's into A, right? If W makes a correct prediction, you just ask the same W again. If the W's makes a wrong prediction, you get a new version of W. You just add a new W into A, right? So finally, we will look at A. A is essentially the summation of each distinct bit vector multiplied by the number of predictions it makes, right? And then if we use A to make prediction on some new example X, we essentially, because this is where we represent A, right? This is a summation of the distinct weak vectors multiplied by the number of their predictions, right? And then multiply with X, right? So it's actually CI WI transpose X. And there's actually a ensemble of the prediction scores of all the distinct weak vectors, and then take the sign. So this is the average prediction. Any question regarding the algorithm steps and also the meaning of A? So everyone is comfortable? Yeah, the benefit of average perception is that it also reflects on some idea, right? But it does not explicitly store all the distinct vectors. Instead, we just store their summation multiplied by their number of predictions. So only store this. Right? This is actually A. And finally, when we use this A to make prediction, the final score we get is actually the weighted summation of the prediction score made by distinct weight vectors during the running. Right? And then we look at the sign of the prediction score. So on one hand, it kind of like inherit the robustness of the weighted perception because they also reflects ensemble learning idea, right? On the other hand, on the other side, we can dramatically reduce the storage cost. We never need to store all distinct vectors explicitly. We never need to count how many times each distinct vector was used. So this is extremely popular. If you want to use perception in practice, use average. And finally, I want to emphasize the difference between the two, right? Although they kind of have the same idea, right? The difference only lies in the final prediction step. If it is weighted perception, because it explicitly stores all the distinct vector, right? It will use every distinct vector to make a prediction. So get -1 and +1, and then give those predictions the votes by the CIs, and then take a look at the final votes. But for the average perception, because we never be able to store WIs and CIs explicitly, we just store their summation implicitly. Right? So when we make prediction, we essentially calculate the voted summation of the prediction scores rather than prediction labels. And then finally look at the voted prediction scores and look at the sign. So look at the concrete example, right? So suppose we have 3 distinct vectors running the voted and average perception, right? So now we want to use W1, W2, and W3, right? To make prediction for a new test example X. Right? So we know that when we use W1 to make prediction, the score is W1, right? S1. W2, the score is S2, and W3, the score is S3. And the count is the same, C1, C2, C3, are all ones. Right? If we use average perception, yeah, we'll find the prediction step. We know that we actually do the voted summation of the prediction scores, right? Meaning that we're going to calculate C1 times S1, C2 times S2, C3 times S3, which is just S1 plus S3 plus S1 plus S2 plus S3, right? And we're going to determine the final label to be positive if their summation is non-negative. However, for weighted perception, it's not like that. We just look at according to the 3 prediction scores, right? As long as 2 of them are non-negative, we're going to predict the final label to be positive. It does not care about the skew of those prediction scores. For example, if S1 is 0.1, S2 is 0.2, S3 is minus 0.4. From weighted perception, we know, okay, according to S1, we're going to predict the example to be positive. According to S2, positive. According to S3, negative. So we have 2 positive predictions, 1 negative according to their votes. Like C1, C2, C3 are all ones, right? So we're going to predict the final label to be positive. But how about the average perception? The average perception actually just the votes on the prediction scores. The votes are all ones, right? We just add them together, we get their summation to be a -1. So the average prediction will give a negative prediction as the final prediction. Any questions so far? Okay, great. So just to emphasize there is difference between the two, right? Which is only expected in the final prediction rule. So now we have finished the discussion about perception. So to summarize, perception is an online learning algorithm for linear classifiers. So it's very widely used, very easy to implement, right? And the weights are updated kind of like additive, right? According and everybody should be clear about the rationale why these updates these updates are reasonable, right? And we also have like geometric interpretation about the rationale about perception updates, and it has a mystic bound which can estimate the number of mistakes before the convergence of perception. And also we have gone through a few practical variants. And if you want to apply perception in your own problem, your research project, your practical, your industry project, please use these practical variants. And also you should be able to implement perception algorithm and in our homework too. Okay, thanks everybody. So I'll see you on Thursday.